producing a loop like this. This is a stationary wave. If you are looking at this, its form does not move. But a progressive wave is a wave whose form appears to be moving. For example, you drop a stone on water, you see the waves spreading out. That's a progressive wave. You hold a rope at one end and you move it up and down with one end fixed to a support. You see a progressive wave. Its form is moving. This is progressive because its form is moving. Progressive wave. And this is a stationary wave. Now, what are some of the differences between a stationary wave and a progressive wave? I've said the form of the stationary wave does not move. The form of the progressive wave moves. The progressive wave has a common amplitude. The amplitude is the same throughout. We are still going to look at amplitude. And a progressive wave, or a stationary wave, the amplitude varies, which means there are areas of maximum vibration and areas of minimum vibration. There are areas of maximum vibration and areas of zero vibration. But for a progressive wave, they have a common vibration. The particles vibrate in similar manner, covering the same distance both up and down. Covering the same distance, all the particles along the wave profile, they cover the same distance up and down. But for a stationary wave, these particles here, they cover a maximum distance, while these particles at the end, they cover very small distance comparatively. We are going to study progressive waves, then I'm going to define other parameters concerning progressive stationary waves and progressive waves. A stationary wave, an example is when a guitar string, when you pluck a guitar string, when you're playing a guitar, you pluck the string is tied at both ends. The stationary wave is set along the guitar. When you blow air across a flute or across a pipe, you set a stationary wave in motion. But when you throw a stone in water, a progressive wave is formed. When you hold a spring at one end and you move it up and down, you shake it, you disturb it, a progressive wave is formed. Now, I want us to define a few terms as far as waves are concerned. At our level, I want us to define a few terms as far as waves are concerned. First, a wave is a vibration that produces a complete cycle. It is a disturbance. A complete wave is a disturbance that produces a complete cycle. But that's not the definition. I'm describing it. I'm not defining it. And so, this is a complete wave. This is a complete wave. It looks like a cycle. If you were to flip this side, if you were to cut, you can carry this face to this. And so it's going to form a loop. It's going to form something like this. It means we can flip this side and it's going to fall here. So you see that it's a complete cycle. A complete cycle makes a wave. That is a wave. Or if I take away this rest position, that is a wave. Now we can increase it to have more than one wave here. This is 1.5. Now if you look at this, on this diagram, there are a few things I want to define just using this diagram. This is called a crest. This point is called a trough. And this point is called a crest. This line is called the rest position. Now, with reference to the rest position, what is actually the rest position? The rest position or the reference position is the position that all the particles will assume when there is no motion. If this is a rope and the rope stops vibrating, all the particles will line up on this. It means that this is like the rope is tied to this support. Now, when you start flipping it up and down, you have this shape form. When you stop the movement, when you stop the disturbance, the rope is going to take this position of rest. Rest means there's no motion. If this is water and you drop a stone on the surface of the water, you'll see the ripples flying up and down, going forward or going out in both directions, depending on the disturbance, the shape of the disturbance. So when there is no motion, all the particles assume this rest position. It means in any vibration, there is always a lowest point reached and a maximum point reached. The lowest point reached by a particle is called a trough on the wave profile, and the maximum point reached by a particle is called a crest. A crest is a point reached, the maximum point reached by a particle above the rest position. the minimum point reached by a particle below the rest position is called a trough. So if I have this one has two crests and one trough. Two crests. Excuse me. This is another crest. This diagram has two crests and one trough. Now I want you to see that this particle is vibrating from rest position right up to this point, and then it returns back and comes right down to this other point. So the wave is vibrating, the particles are vibrating within this distance. All the particles are moving up. This particle here is moving up and down. This one here up and down. All the particles up and down, they are moving within this maximum space. Now, the maximum displacement from rest, this is the maximum displacement from rest. It is called the amplitude. You can also define it as the minimum displacement from rest. It's called the amplitude. What's the difference between the amplitude and the crest? The crest is a position, it's a point reached by a particle. And the amplitude is displacement. Amplitude is measured in distance, but crest is just a point. The crest is just a point. And the amplitude is maximum displacement from rest, or above the rest position, or minimum displacement below the rest position. If that is taken care of, if that is noted, I want us to define the next term, which is the wavelength. The wavelength is just the horizontal distance measuring the length of the wave. I said this is a complete wave. If you permit me to take this off, this is a complete wave. So what is the length of this wave? It's not going to be all of this distance. No, it's the horizontal distance covered by the length. The symbol of wavelength is lambda. How do you spell it? Lambda. It's the symbol of wavelength. The symbol of wave is the distance covered by a complete wave. The distance covered by a complete wave is the wavelength. If I put back the portion that we had, a wavelength can also be the distance between two successive crests. The distance between two successive crests. This is a crest, C1. This is another crest, C2. So the distance between C1 and C2 is yet another wavelength. If we had a trough down here, the distance between any two successive or neighboring troughs is also a wavelength. So the distance between any two neighboring crests or neighboring troughs is a wavelength. So the distance between C1 and C2, distance between C1 and C2 is equal to lambda. The distance between C1 and C2, the distance is equal to lambda. But the distance between C1 and C3 is equal to 2 lambda. This is now the distance between the first crest, the second crest, and the third crest. It's 2 lambda. So wavelength is the distance of a complete wave, the distance covered by a complete wave, or the distance between two successive crests or two successive troughs. We are going to still define it as far when we get to particles in phase. It is good that we also talk on particles in phase. Particles in phase. Excuse me. Okay. We will also talk of on particles in phase. Considering this diagram, if this particle, this is particle 1, A, B, C, D, E, F, G, H, E. This is another particle. Yes. These are vibrating particles. Consider this to be vibrating particles along the wave profile, such that this particle is moving down. This particle here is moving down. This one here is moving down. This one is moving up, 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 down, down,